Let me begin the module by explaining how air conditioning compressors are used in buildings. Commercial buildings require cooling to offset heat gains from the internal and the external sources. Internal heat gains include lights, people, and office equipment. External heat gains include solar radiation and outdoor air temperature. Air conditioning cooling systems remove heat from the space and reject it to the outdoors. The air conditioning cooling systems are classified under 3 broad categories. They are central air conditioning systems, packaged air conditioning systems, and individual air conditioning systems. First, let's have a look at the central air conditioning systems. Central systems are those in which cooling is generated in a chiller and distributed to air handling units with a chilled water system. These systems have primary and secondary pumps to deliver chilled water throughout the building. These systems also have cooling towers and condenser water pumps to reject heat. Chilled water is distributed to cooling coils for distribution throughout the building by air handling unit supply and return fans. Next, we shall see the packaged air conditioning systems. Packaged systems are factory-built and have a direct expansion cooling coil with an air-cooled condenser unit to reject heat. The packaged systems typically do not use chilled water as the cooling medium. The cooling is delivered directly to the supply air in a refrigerant cooling coil. The heat picked up from the cooling coil is rejected in a air-cooled condenser coil directly to the outside air. Now, we shall see the individual air conditioning systems. Individual air conditioning systems are self-contained, packaged cooling units mounted in windows or on the external walls such that the cooling occurs indoors and heat rejection occurs outdoors. The units are designed to provide the total cooling for a room or zone. The units are used in small zones or on the perimeter of buildings. They may be combined with other HVAC systems for control of building temperatures. The units include refrigeration components, outdoor louvers, dampers, in some units, fans, and controls. Now, we shall see the various types of air conditioning compressors used for cooling systems. In commercial air conditioning, the major compressors used are reciprocating, scroll, screw, and centrifugal. Compressor sizes start with reciprocating and scroll, thus the smallest, 3 to 175 kilowatts, followed by screw, 75 to 1,400 kilowatts, and centrifugal, thus the largest, 1,400 kilowatts and larger. Capacities listed are typical and may involve multiple compressors. Reciprocating, screw, and scroll are all classified as positive displacement compressors because the refrigerant chamber is actively compressed to a smaller volume. In screw and scroll compressors, this is a twisting or rotational action. In reciprocating compressor, it is the linear stroke of piston reducing the volume of the cylinder holding the refrigerant gas. The centrifugal compressor is a non-positive displacement type. It raises the pressure and temperature of the refrigerant by converting kinetic energy into pressure. Central plants usually have centrifugal chillers because of their large size. Screw compressors are most popular in the mid-size market and smaller, but they do not have the high part load efficiency of scroll compressors. Scroll compressors are becoming more prevalent in the HVAC industry. They have excellent reliability, high efficiency, low sound, low vibration, and better capacity control over a range of operating characteristics when compared to reciprocating and screw compressors of similar size. The Danfoss VLT HVAC drive has been engineered with a number of features to provide capacity control of scroll compressors through frequency control. Next, we shall have a look at the screw compressor operation. A screw compressor operates by using paired rotors machined to extreme accuracy of pitch and thread form to provide non-pulsating, positive displacement compression. Screw compressors have two precision machine rotors which rotate to compress the gas. Take a look at the illustration. It shows a male rotor and female rotor. As the rotors turn, the suction phase begins as a space opens at the top when the two rotors unmesh. As the rotors continue to turn, the interlobe space increases in size, and the gas is drawn in through the inlet port. The suction is sealed off by the meshing of the rotors as they continue to turn. In the compression phase, further rotation meshes the male and female lobes and reduces the interlobe volume. At a point, the gas is fully compressed and the discharge port is uncovered. The compressed gas is discharged and the compression cycle is completed. The typical capacity reduction method of control is a slide valve with a sliding action parallel to the rotor bores. They are placed close to the high-pressure discharge port and bypass a portion of the trapped gas charge back to the suction. This method of capacity control provides good part load performance without reducing the full load capacity. Next, we shall have a look at the scroll compressor process. Take a look at the illustration. It shows the mating and volute scrolls in a spiral shape that mesh. The upper scroll is fixed in place. An eccentric motor shaft moves the lower scroll in an orbital pattern within this fixed scroll on a rotor. In the compression process, the upper and lower scroll vanes form crescent-shaped pockets. As the lower scroll orbits, the sealing points on the vanes migrate inward, pushing the crescent-shaped pockets toward the center. As the pockets move, they decrease in volume and compress the trapped gas. Take a look at the illustration. It shows the sequence of orbits and the movement of the trapped gas pockets. In the first orbit, suction, as the bottom scroll orbits, two pockets of suction gas are formed and enclosed. Blue area. During the second orbit, compression, the pockets of gas are compressed as the volume is reduced. Green area. In the third orbit, the two pockets of gas are compressed further and discharged simultaneously through a small port opening in the center of the fixed scroll. Red area. With this, the scroll compression process is complete. Standard capacity control of scroll compressors is accomplished by installing multiple compressors in a single chiller to provide capacities of up to 175 kilowatts. Compressor volume control can also be accomplished by reducing the speed of the motor. The Danfoss VLT HVAC drive has been designed to provide speed control of scroll compressors. Next, we shall have a look at reciprocating compressor operation. Reciprocating compressors use pistons that are driven directly through a pin and connecting rod from a crankshaft, similar to an automotive reciprocating engine. The most important components in a reciprocating compressor are the suction and discharge valves. Suction process. At the beginning of the suction phase, the piston is drawn down in its cylinder, opening the suction valve, and vapor refrigerant is drawn into the cylinder. When the piston reaches the bottom of the stroke, the suction valve closes, trapping the suction volume. Compression process. The compression process is started when the piston is starting up the cylinder and begins compressing the gas ahead of it as the volume is reduced. Discharge phase. The discharge phase begins when the discharge valve first opens. As the pressure in the cylinder exceeds the pressure above the valve lifts, allowing the compressed gas to be pushed in the discharge manifold. The discharge process is complete when the piston reaches the top of the compression stroke and the discharge valve closes. There is always a small amount of clearance volume left at the top of the stroke to expend on the next suction stroke. Capacity control. The most common used method of control is bypassing the refrigerant gas with unloaders within the compressor. Next, we shall have a look at centrifugal compressor operation. Centrifugal compressors have long been used in larger water chillers. High efficiency, superior reliability, reduced sound levels, and relatively low cost have contributed to the popularity of the centrifugal chiller. The capacity of a centrifugal chiller can be modulated using inlet guide vanes. A combination of inlet guide vanes and a variable speed drive control are now being applied to new centrifugal water chillers. Existing centrifugal chillers must be studied carefully to determine if they can be controlled with variable speed drives. Using a variable speed drive with a centrifugal chiller may degrade the chiller's full load efficiency. Centrifugal compressors, sometimes called turbo compressors, continuously exchange angular momentum between a rotating impeller and a steady flowing refrigeration fluid. Because flow is continuous, these machines have greater refrigeration capacity than positive displacement devices. The suction flow enters the rotating impeller and is discharged radially at a higher velocity. A centrifugal compressor can be single-stage, having one impeller, or it can be multi-stage, having two or more impellers. The suction gas passes through a set of adjustable inlet guide vanes before entering the impeller. As inlet guide vanes open, more gas passes through the compressor. The vanes are used for capacity control, similar to inlet guide vane control of centrifugal fans. Capacity is varied by swirling the refrigerant entering the impellers. The inlet guide vanes produce this swirl. Setting the vanes to swirl, the flow in the direction of impeller rotation produces a near compressor performance curve without a change in speed. Controlled positioning of the vanes can be done using pneumatic, electric, or hydraulic actuators. Next, we shall look at the refrigeration cycle. To understand the refrigeration cycle, a typical air-cooled process, along with the pressure enthalpy, total heat content, pH diagram for a refrigeration circuit, is shown. The pH diagrams have different shapes and values depending on the compression cycle and the refrigerant used, but in general, the shapes of the curves are similar. Each refrigerant has a slightly different shape of the curve, and the compression portion of the curve varies by the compressor type. Take a look at the illustration. It relates the typical refrigeration components to the pressure enthalpy diagram for a refrigeration cycle. Instead of chilled water flowing through the tubes of the cooling coil, packaged systems have cold liquid refrigerant flowing through the tubes. In this case, the fin tube cooling coil is the evaporator or direct expansion cooling coil of the refrigeration loop. As air passes through the coil, heat is transferred from the air to the refrigerant. This heat transfer causes the refrigerant to boil and exits the evaporator as vapor. The evaporator process is from point 1 to point 2. Heat from the building is being absorbed as a latent energy phase change. The refrigerant changes from a liquid to a gas in this phase change, and the pressure and temperature remains constant. Next in the cycle, a compressor raises the temperature and pressure of the refrigerant, so the heat absorbed by the evaporator coil can be rejected to the outdoors by the condenser. The line from point 2 to point 3 represents the compression process. The change in pressure is called lift. The greater the lift, the more work, power, the compressor produces. The compressor simply compresses the gas, and by doing the work, adds sensible heat to the gas, increasing the enthalpy. A typical air-cooled condenser has the hot, high-pressure refrigerant vapor flowing through the tubes of a fin tube heat exchanger, and uses propeller-type fans to draw outdoor air over the outer surfaces of the tubes and fins. The condenser is a heat exchanger that removes heat from the refrigerant, causing it to condense from a gas to a liquid. The gas enters the condenser at point 3. The refrigerant is cooled by the outside air until condensation occurs, and the gas changes to a liquid, point 4. Like the evaporator, the pH diagram line is horizontal, indicating constant pressure and temperature. The thermal expansion valve, TEV, provides a pressure drop and chills the liquid refrigerant as it passes through the valve. This is the vertical line from point 4 to point 1, completing this cycle. Now, the refrigerant is chilled and ready to pass through the evaporator to begin the cycle again. We have discussed various compressors and capacity control. However, before proceeding with applications, it is important to note that capacity control of compressors is complex and have important considerations, such as minimum speed required for proper lubrication, or maximum speed to prevent carryover of lubricant into the vapor stage of a compressor. Application of frequency converters to compressors require approval of the compressor manufacturer. Application to new compressors is the major market for speed control using frequency converters. Existing compressors should not be converted without a careful engineering study and coordination with the compressor manufacturer. Speed control of compressors should be done only if information and approval is available from the compressor manufacturer. Trends in the HVAC market are for manufacturers to produce smaller, packaged air-cooled equipment with multiple compressors. Typically, scroll and screw compressors are used. Scroll compressors have cycling on and off of compressors for capacity control, while screw compressors use a slide valve. The new packaged equipment market, where an HVAC manufacturer is using a compressor capable of variable speed, is the ideal application for the VLT HVAC drive. We shall now look at the traditional packaged air conditioning system. The illustration shows the typical packaged unit used for cooling a building. The air is circulated from the conditioned space through the unit and back. Outside air is used for free cooling when the outdoor temperature is cool enough and to meet requirements for minimum outside air. Outside and return air dampers mix the amount of air to provide a constant volume of air to the space. The air moves through the filter and cooling coil and is applied to the space through ductwork and supply diffusers. Here, you can see that the air is being returned through the sealing plenum, although it can be returned through ductwork. The evaporator section consists of the evaporator, direct expansion cooling coil, and supply air fan. The room thermostat controls the cooling by modulating or cycling on and off the compressor. Frequent on and off of the compressor results in the wear and tear of the unit and increases the power consumption. The condensing section, consisting of the refrigerant compressor, condensing coil, and condensing fan, can be connected to the unit, as shown, or located externally, with the refrigerant piped between them. Some units have variable air volume, fan speed control, if the evaporator face velocity is high enough to prevent coil condensate from freezing on the face of the coil. Packaged air conditioning equipment with multiple scroll compressors vary refrigeration capacity by staging on and off multiple compressors. Take a look at the graph. It shows how capacity is increased as additional stages are added for cooling. Additional compressors are added as the cooling load increases. On a reduction in cooling load, a compressor is turned off to match the reduced load. The VLT-HVAC drive, with cascade control, provides the sequencing needed without additional control components. We just saw the working of a traditional, packaged air conditioning system. You have seen that, in the traditional method, a cycling of the compressor results in the wear and tear of the equipment. Variable speed control of a compressor provides improved efficiency over cycling of a compressor. That is where Danfoss solution comes into play. In Danfoss solution, the best energy savings are achieved by installing a VLT-HVAC drive to the system. Danfoss has a new approach in the design of speed control for compressors. By varying the speed of a compressor, the capacity of the compressor is varied. With scroll compressors, the relationship between speed and capacity is almost linear. Double the speed, and the capacity is approximately doubled. Danfoss capacity control. For periods of high cooling demand, the input frequency of the compressor can be increased. For periods of lower cooling demand, a lower input frequency to the compressor is supplied. Periods of normal cooling demand use the standard 50 or 60 Hz frequency. Maximum required cooling capacity is achieved using 90 Hz for scroll compressor speed. Minimum required cooling capacity is achieved using 30 Hz for scroll compressor speed. How can we increase the frequency higher than the power supply frequency? To run a compressor at a higher frequency than the power supply frequency. For example, on 230 volts, 50 Hz, it is necessary to supply a higher voltage to the motor. For 90 Hz frequency, we need to supply higher voltage. With 230 volts at 50 Hz, for 90 Hz, we need 230 times 90 by 50 is equal to 415 volts. This is supply voltage into the VLT-HVAC drive at 50 Hz. Take a look at the graph. It shows the relationship for scroll compressor voltage, capacity, and Speeds between 30 and 90 Hz. 30 Hz is the minimum speed required for proper compressor lubrication, while 90 Hz is the maximum speed to prevent oil carryover. Using this method of capacity control, we can replace the 3 small compressors in the standard solution with a larger capacity compressor and operate it at variable speed. In Danfoss solution, the room thermostat senses the temperature and sends a signal to the VLT/HVAC drive, which in turn controls the speed of the compressor, providing a variable amount of cooling capacity to the room, while maintaining the temperature. Take a look at the graph. It shows the capacity control of the variable speed compressor. With Danfoss solution, one larger variable speed compressor can provide the cooling for 3 of the smaller compressors. Scroll compressors have higher part load efficiencies to provide a better energy rating for the equipment and energy savings during operation. Additional savings can be obtained by an equipment manufacturer by furnishing 1 compressor with associated piping and control instead of 3. Improved energy ratings are important to equipment manufacturers because of new energy codes being introduced. Some new packaged air conditioning systems include variable air volume, fan speed control, and variable speed compressor control. A frequency converter is provided to control fan speed, as in a standard VAV system. Fan speed is controlled by a duct static pressure sensor in response to the demands of room VAV boxes. In the packaged system control application, the evaporator, or direct expansion coil, replaces a cooling coil. A temperature sensor is installed in the supply air duct to the VAV boxes. A digital controller varies the speed of the compressor through the VLT/HVAC drive to maintain a constant supply air temperature. We just saw that the Danfoss solution facilitates energy savings in the application. Take a look at the graph. It shows the comparison of energy consumption for a Danfoss and traditional method of controlling a single compressor. You can see from the graph that the power consumption is lower in the Danfoss solution, thereby resulting in more energy saving as compared to the traditional method. Typically, 15 to 20% electrical energy can be saved for the compressor alone. The level of energy savings depends on the load profile of the system, the sizing of components, that is, an oversized compressor or multiple compressors. Energy savings are also dependent upon the type of refrigerant and the lift or pressure rise provided by the compressor. Energy savings are due to higher evaporating temperature and lower condensing temperature, leading to improved COP, coefficient of performance. Let's go in for a quick check of your understanding. Apart from the advantages of energy savings, there are some key features that improve the performance of this application. Let us see these key benefits of compressor control, one by one. Precise and smooth temperature control by capacity modulation. The system is more stable due to control of evaporator and condenser pressure. Stable control and better performance provides additional energy savings. Noise is reduced from compressor operation at slower speeds. Fewer start or stop cycles of compressors increase lifetime and reduced wear and tear. No inrush currents at startup. Soft start. Before ending this module, let me give you a brief summary of what we learned. We saw the 3 types of air conditioning systems, and also saw the various types of compressors used in air conditioning. We also saw the typical refrigeration components applied to the pressure enthalpy diagram for a refrigeration cycle. In the traditional method, we saw that the room thermostat controls the cooling by cycling on and off the compressor, thereby resulting in wear and tear of the unit and higher power consumption. But in Danfoss solution, we saw that the VLT-HVAC drive controls the speed of the compressor, providing a variable amount of cooling to the room, while maintaining the temperature and saving energy. Finally, we saw additional key benefits achieved through Danfoss solution. We have completed the module. By now, you must have gained a good idea of compressor applications in general, how it works traditionally in Danfoss solution, the key benefits achieved through Danfoss solution,